Okay, this may be the last video for our machine learning using R series. And in this video, I want to talk about regression and classification using shallow neural networks. So again, the shallow neural network means that we only have one hidden layers. Okay. All right. So we need a couple of R packages, nnet for shallow neural networks, NeuralNet for visualizing and custom training, and we want the caret for data splitting and evaluation. And also we need NeuralNetTools for plotting relative importance. Let's see here. I'm gonna load these four libraries, set a random seed, create a data set with 500 sample size, and 3 continuous variables, 2 categorical variables. Okay. Okay. So we can create dependent variable. So one is for continuous dependent variable for regression, and then a 3-level categorical dependent variable for classification. Right. And first we can do pre-processing by scale continuous variables. We can use a function called the pre-process from caret. And these are used to estimate transformations like scaling, centering, or range normalization based on the training data. Okay. After that, we can just scale the data doing predict using this prep proc values and then scale the data frame. Then we can split into training and the test data set. All right. Now we're going to show how we're going to do a neural network, shallow neural network for regression. So use the function nnet. Okay. So you put the dependent variable target reg, regressed on continuous 1 plus continuous 2 plus continuous 3 plus categorical predictor 1, categorical predictor 2. Data go to training data, size go to 5. Now here means we use 5 neurons. Usually the rule of thumb is the number of inputs plus the number of outputs and divided by 2. Or you can do a grid search for the optimal size. Okay, so here we just assign 5 neurons. Okay, and linout equal to true. And if you want a regression, then you specify linout equal to true. Okay, and then trace equal to false and maximum iteration 500. It converts it quickly. Maybe we don't need 500 iterations. And then we can do prediction using the function predict, using the fitted neural network regression model on the test data set. And then there is a function called the post resample from caret for automatically assessment of accuracy of regression word classification. Okay. So we just use that. And you can see it gives us RMSE, R squared, and MAE. Okay. So pretty neat function. Okay. All right. The next one is I want to show you how to do classification. And we still use the function nnet. And then the syntax would be target class regress on continuous 1 plus continuous 2 plus continuous 3 plus category predictor 1 plus category predictor 2. Data equal to training data. Size equal to 5. Now here, linout equal to false. If you want classification, you specify false. Okay. Trace equal to false, and maximum iteration 500. And also takes no time. Okay. And we can do prediction, predict the classes. You have to use the predict function and nn class on test data set and type equal to class. Okay. And then you can do accuracy assessment for the classification. If you just use post resample function, it just gives you overall accuracy 0.69, so that's all correctly classified, number of all correctly classified cases. And the kappa equals 0.47, that's the agreement. Okay. But if you want more kind of accuracy assessment metrics, you can use the confusion matrix function, and it has to use the factor of predicted class on the test data set on the target class. Okay, so you can see it give you a whole bunch of outputs here. So first, it gives you the confusion matrix. So the prediction is high, low, medium, and references high, low, medium. And you can see on the diagonals, those are the correctly classified cases. Off diagonals are incorrectly classified, misclassified. Then the overall statistics, the accuracy is the total number of correctly classified cases, 0.619, and 95% confidence interval for that accuracy. And the number of information rate or no information rate, NIR is 0.45, and this is it's called the no information rate, which is the accuracy you would get by simply guessing the most frequent class. In this case, high. You just say every case is high every single time, then you get 0.45. So that's kind of a benchmark. And then the p-value of the accuracy of your classifier greater than the NIR rate is fairly small. So you do have a classifier much better than the benchmark. Okay. And the kappa is the agreement rate, 0.47. We don't have the McNamara test. And then down here, you can see a couple of the table for statistics by class. You got sensitivity, specificity, and positive predict value, negative predicted value by class. Okay, you can see, for example, sensitivity is very high in the high class. Specificity is very high in the low class. And the prevalence is relative frequency in the data. And the detection rate is sensitivity times prevalence. So you can see the detection rate is pretty good. Is it good? No. Let me see here. Detection rate is not very good, actually. It's 0.41 in the high classes, and in the low class, it's only 0.6. Okay, 0.06. Okay, and detection prevalence is the predicted relative frequency. You compare to the prevalence, they're also pretty different. Okay, so these are really not very good. And then the balanced accuracy is the most important index. Is the average of the sensitivity and specificity. So you got 0.79, 0.783, and 0.66. So average. Okay. So okay. And then we can do some visualization. First, you just use the function plotnet to get the architecture. So you can see here the architecture. You have the left is the input layer. You got 5 variables. The variable name for the categorical ones are kind of cut off. Okay, so I don't know why. And then you got the hidden layer. You got 5 hidden nodes there, H1 to H5, and you got one output layer, which is O1, just one target variable. And you can see the predict 1b, that's actually the dummy variable for the first categorical predictor. Oh, and B1, B2 are biased, so they're like intercept for that regression model. And also the darker and thicker lines, they mean higher weights, and the lighter colored and thinner lines means lower, small weights and unimportant. Okay. Okay. And we can also plot out the relative importance. You can see it's called the Garson plot. So you can see the continuous variable 3 is the most influential predictor. Okay. Okay. I think this is a very straightforward and simple demonstration of regression and classification using shallow neural network. And also, it seems that it's pretty awkward in R to try to implement deep neural network, but I'm gonna still give it a try, but I'll try to make a separate playlist. Thanks for watching, and this will be the end of our series on machine learning using R. Hope you like it.